Number of relations from A to B is equal to 2 to the power of n of A into n of B. That means 2 to the power of number of elements in A and number of elements in B. That is 2 to the power of m into n. If no element of A is related to any element of A, that is denoted as null set. 2 to the power of 3 into 2 is 2 to the power of 6. So 2 to the power of 3 into 2 is 2 power 6, that's equal to 64. Hello dear students, welcome to this session of mathematics class. I am Mr. Niranjan, faculty, Department of Mathematics, Vidhyaashram PU College, the Temple of Excellence. Now in this session today I am going to discuss the revision for the first important chapter, relations and function. So this is very important chapter. Now before going to the exact chapter, let us know regarding the weightage for this chapter for this academic year, that is for this 2022 examination. This is for 2022 examination. The weightage for this chapter, relations and functions, is relations and functions. The weightage is like this. You will have 2 mark 2 questions, 2 marks questions, 2 questions, 2 marks, again 1 2 mark question, again 1 3 mark question, and there are 2 5 mark questions from this. So the question number of part D, the first and second questions are from this part only. That is, you will get 2 5 mark question, 10 plus 3 plus 2 plus 2. Totally, you will have 17 marks. The weightage for this chapter is 17 marks. You will have 2 1 mark question, 1 2 mark question, and 1 3 mark question, and 5 mark 2 questions from this chapter. The weightage will be the 17 marks. Very easy to score 17 marks from this chapter. Now, let me discuss few problems in 1 mark, 2 marks, 3 marks, as well as in 5 marks. Okay. Now, let us come to the first concept, Cartesian product. So what is a Cartesian product of two sets? Before going to the exact definition of a relations and function, let us know regarding the Cartesian product. What is Cartesian product of two sets? Suppose if A and B are any two non-empty sets, then the Cartesian product of A and B is denoted as A cross B. A cross B is a set x comma y such that x belongs to A and y belongs to B. That means first member is an element of A and second member is an element of B. So A cross B, the Cartesian product of A and B is denoted as A into B. A cross B is equal to a set x comma y such that x belongs to A and y belongs to B. That means first member is an element of A and second member is an element of B. Now let us consider a small example. Let us consider if A is equal to 1, 2, 3, 3 elements and B is equal to x comma y 2 elements, then the Cartesian product of A and B is A cross B is equal to 1 comma x, 1 comma y. Similarly, 2 comma x, 2 comma y. And next is 3 comma x and 3 comma y. So all the ordered pairs will form a Cartesian product A cross B. So 1 comma x, 1 comma y, 2 comma x, 2 comma y, 3 comma x and 3 comma y, the ordered pair. Suppose if A comma B belongs to R, means we say that A is related to B under the relation R and it is denoted as A is related to B. That is, A comma B belongs to R. Now let us take one more example. Suppose if A is equal to, let me take A is equal to 2 and 3 and B is equal to 4 comma 5. Then how to write the Cartesian product of these two? A cross B is equal to the set 2 comma 4, then same 2 comma 5. Similarly, next 3 comma 4 and 3 comma 5. So this is the Cartesian product of A and B. Okay. Now let us come to the relation. Now a definition of a relation. Now let us know what is the definition of a relation. A relation or on a set A and B is the subset of A cross B. A relation or on a set A and B is a subset of A cross B and it is denoted as R. A relation from A to B, a relation from the set A to set B. The relation on a set A and B is the subset of the Cartesian product A cross B and it is denoted as R. The subset of the Cartesian product, the subset of A cross B is called the relation and it is denoted as R. Now let us consider an example. Now let A is equal to, suppose if A is equal to 1, 2, 3, B is equal to 2, 3 and 4, define a relation R from A to B as R is equal to x comma y set of all ordered pairs such that x is less than y. First element is less than the second element. What is the given condition? X is less than y. So x is less than y is the condition. Write out the cross product for this. So just write down A cross B. What is A cross B? A cross B is the set of all ordered pairs. First write down the Cartesian product A cross B, then we will write the relation. What is A cross B? 1, 2, 1, 3, 1, 4. Similarly 2, 2, 2, 2, 3 and 2, 4. Similarly 3, 3, 2, 3, 3 and 3, 4. This is A cross B. The Cartesian product of A and B is A cross B. Now, just take, now what is the relation given? The relation is defined as x comma y such that x is less than y. The set of all ordered pairs in which first element is less than the second element, x is less than y. So here 1 is less than 2 you can take, 1 is less than 3 we can take, 1 is less than 4. Similarly 2 is greater than 1 we cannot take, whereas 2 is greater than 1 we cannot take this, and 2 is less than 3 we can take, 2 is less than 4, 3 is greater than 2 we cannot take, 3 is equal to 3 we cannot take, and 3 is also greater than 4. So only these elements, that is the relation contains 1, 2, 1, 3, 1, 4, 2, 3 and 3, 4. See, observe carefully, all the elements of R are the elements of set A cross B, right? All the elements of R are the elements of set A cross B. That means A cross B contains all these elements. That means R is the subset of A cross B. So here R is the subset of A cross B, right? That is what? A relation R on a set A and B is the subset of A cross B. R is the subset of A cross B. That means all the elements of the relation are the elements of the Cartesian product A cross B. Therefore, a relation R is a subset of A cross B if a set is defined from A to B. That is, a relation R on a set A and B is a subset of A cross B denoted as R. This is an example for the relation. So, therefore, R is the subset of A cross B. Now, let us come to some important concept. So, there are some important concepts. You may expect this type of problems for 1 mark or 2 marks. Suppose if A and B are any two, the number of relations from A and B, A to B, if A and B are any two sets, non-empty sets, then the number of relations from A to B, the number of relations from A to B is given by number of relations from A to B is equal to 2 to the power of n of A into n of B. That means 2 to the power of number of elements in A and number of elements in B. That is 2 to the power of m into n. Number of elements into A and number of elements into B. Suppose if A contains m elements and B contains n elements, then the number of relations from A to B is 2 to the power of m into n. So, the number of relations on A, if it contains only one set, then the number of relations on A is 2 to the power of n into 2 to the power of n. That is nothing but 2 to the power of n square, or 2 raised to n, 2 to the power of n A into n A, that is 2 to the power of n square. Okay. So, the number of relations from A to B is 2 to the power of m into n, and the number of relations from A to A itself is 2 to the power of n of A into n of A is nothing but 2 to the power of n into n is 2 to the power of n square. 2 to the power of n square, right. Now, let us take an example. This is very important concept for 1 mark. Find the number of relations from, number of relations on the set A is equal to 1, 2, 3. Since here this set contains how many number of elements? It contains 3 number of elements. So, the number of relations from the set A to A is 2 to the power of n square, or 2 to the power of m into n, that is 2 to the power of 3 into 3, that is 2 to the power of 9. 2 to the power of 9 is nothing but 512. Okay. Here n contains only 3 number of elements. So, according to the definition, according to the formula, find the number of relations from on A to A. So, the number of relations on A to A is 2 to the power of n into n. That is n is 3 and n is 3. 3 into 3 to 3 is 9. 2 to the power of 9 is equal to 512. This is very important for 1 mark. Similarly, let us take one more question. Find the number of relations from A to B. So, here A contains 1, 2, 3, B contains 2 elements x and y. So, the number of elements in A is m is equal to 3 and the number of elements in B is 2. So, m is equal to 3 and n is equal to 2. Therefore, the number of relations from A to B is 2 to the power of mn. that is 2 to the power of m into n is nothing but 2 to the power of 3 into 2 is 2 to the power of 6. So 2 to the power of 3 into 2 is 2 power 6, that's equal to 64. So number of relations from A to A is 2 to the power of 3 into 2 to the power of 3, 2 to the power of 9 is 2 to the power of 9 is 512, that is 2 to the power of m into n. Again, if the number of relations from A to B is again same of the form 2 to the power of m into n, that is 2 to the power of 3 into 2 is 6, 2 power 6 is 64, that's it. Okay, now let us come to the next types of relation. Now, types of relations, you may expect 1 mark question from this. For 1 mark, you will have one definition for 1 mark. Yes, now first one is an empty relation. Empty relation means nothing. A relation or on a set A is called an empty relation if no element of A is related to any element of A, that is denoted as null set. Empty relation R is equal to null, which is the subset of A cross A. A relation. So, a relation R on a set A is called an empty relation if no element of A is related to any element of A. No element of A is related to any element of A, that is a relation R is equal to null set, empty relation if null set which is the subset of A cross A. Now let us consider, for example, A is equal to 1, 2, 3, 4. Consider a relation R on a set A defined by R is equal to A comma B such that A minus B is equal to 10. So if you subtract two numbers, you should get it as 10. Now, what are the elements here? 1, 2, 3, 4. If you subtract 1 minus 2 is equal to minus 1. Again 2 minus 3. 2 minus 3 is minus 1. 3 minus 4, that is also equal to minus 1. So, if you subtract any element A to A, you won't get it as 10. So, does not belongs to 10, not equal to 10. So, that means here R is a null set. No element satisfies the given condition that A minus B is equal to n. So, that means R is an example for a empty relation. Here, let us consider a set A is equal to 1, 2, 3, 4 and a relation R on a set is defined by R is equal to A comma B such that A minus B is equal to 10. The difference between two numbers is 10 is an empty relation because no element satisfies the given condition. Therefore, it is an empty relation. That means a relation R on a set A is called an empty relation if no element of A is related to any element of A, that is R is equal to null set, that is R is equal to empty relation which is the subset of A cross A. Now, let us come to the next universal relation. Universal relation means a relation R on a set A is called universal relation if each element of A is related to every element of A. If each element of A is related to every element of A, that is R is equal to A cross A. R is equal to the Cartesian product of A and A. So, if every element of A is related to each and every element, that is if each and every element is related to every element of A, that is R is equal to A cross A. Now, let us take an example for a universal relation. So, a relation on a set A, what is A? 1, 2, 3 given by A comma B such that sum of two elements is less than 10, A plus B is less than 10 is an example for a universal relation. Now, what is the condition given here? A plus B is less than 10, this is the condition. Now, if you add, see, write down the cross product A cross A, that is A cross A is equal to A to A. A is equal to 1, 2, 3. Again, another A is also equal to 1, 2, 3. Write down A cross A. A into A is equal to 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2 and 3, 3. This is what you are going to get. A is equal to A cross A. The Cartesian product of A to A is 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2 and 3, 3. Now, what is to write? Sum of two elements is less than 10. So, this is the given condition. First, sum of these two elements. 1 plus 1 is 2 less than 10. Okay, we can take R. Yeah, again, 1 plus 1, 1 plus 2, 1 plus 2 is 3 which is less than 10. Again, 1 plus 3 is 4 less than 10. 2 plus 1 is 3 less than 10. 2 plus 2, 4 less than 10. 2 plus 5 which is also less than 10. 3 plus 1, 4 which is less than 10. 3 plus 2, 5 and 3 plus 3 is 6, which is also less than 10. So, all the elements of A cross B are in the relation R. So, therefore, this R is the universal relation, that is R is equal to A cross A itself. So, here a relation R on a set is called universal relation if each element of A is related to every element of A, that is R is equal to A cross A. See, all the elements of the relation are the elements of the set A cross A, therefore, R is the universal relation. Here R and A cross A are same, therefore, R is the universal relation. Empty relation and the universal relations are called as the trivial relation. An empty relation as well as an empty relation, and the universal relation are called as the trivial relations. Now, let us come to the next types. So, these are very important types of relations, that is reflexive relation, symmetric relation and a transitive relation. This is very important. You may expect one question from this type of relation. Now, reflexive relation. What is reflexive? So, a relation R on a set A is called reflexive relation if A comma A belongs to R for every A belongs to A, small a belongs to capital A. So, A comma A, B comma B, same elements X comma X, Y comma Y, they all comes under the reflexive relation. A relation R on a set A is called a reflexive relation if A comma A belongs to R for every A belongs to A comma A, 2 comma 2, 3 comma 3, they all comes under the reflexive relation. Next, symmetric relation. Symmetric relation means if A comma B belongs to R implies that B comma A belongs to R for all AB belongs to A. Suppose if A and B are any two elements of the set, then if A comma B belongs to R implies B comma A belongs to R, then it is called as the symmetric relation. If 1 comma 2 belongs to R implies 2 comma 1 also belongs to R, means then it is called a symmetric relation. So, reflexive means A comma A belongs to R. Symmetric relation means A comma B belongs to R implies B comma A also belongs to R for a symmetric relation. This is reflexive. Next, transitive relation. For any three elements A comma B comma C belongs to R, if A comma B belongs to R and B comma C belongs to R implies that A comma C also belongs to R. That means for all A, B, C belongs to R, if A comma B belongs to R and B comma C belongs to R, then A comma B belongs to R, B comma C belongs to R implies A comma C also belongs to R. So, that is, suppose if for example, so 2 comma 4 belongs to R and 4 comma 8 belongs to R implies this 2 and 8 also belongs to R. Okay. So, this is an example for a transitive relation. So, in general, a relation R on a set A is called reflexive if A comma A belongs to R for all A belongs to A. Symmetric if A comma B belongs to R implies B comma A also belongs to R for all A comma belongs to the set A. And transitive property, transitive means if A comma B belongs to R and B comma C belongs to R implies A and C also belongs to R, A comma C belongs to R for all A comma B comma C belongs to the set A. So, that is called reflexive, symmetric and transitive. In these are very important types. So, reflexive, symmetric and transitive. Now, suppose if a relation satisfies all the three relations, reflexive relation, symmetric relation and transitive relation, then such a relation is called an equivalence relation. Equivalence relation. A relation R on a set A is said to be equivalence relation if R is reflexive, symmetric and transitive. If R is reflexive, symmetric and transitive, then that relation is called an equivalence relation. Very important. Define an equivalence relation means a relation R on a set A is said to be equivalence relation if R, that relation R is reflexive, symmetric and transitive. Now, let us consider for example. Let me take an example. Let T be the set of all triangles in a plane with R a relation in T given by R is equal to T1 comma T2 such that T1 is congruent to T2. First triangle is congruent to the second triangle. T1 is congruent to T2. Show that R is an equivalence relation. Now, This is the problem for 3 marks. Now here, what is the problem given? Let T be the set of all triangles. Let T will denote the set of all triangles in a set of all triangles in a plane, and the relation R is defined by, R is given by T1 comma T2 such that T1 is congruent to T2. First triangle is congruent to second triangle. So now let us come to the solution. First, verify whether it is reflexive, symmetric and transitive. If all these three conditions are satisfied, then that relation is called an equivalence relation. Now let us come to the reflexive. R is reflexive. Since every triangle is congruent to itself, every triangle is congruent to itself. This is a triangle, this is congruent to itself. So therefore, T1 comma T2, T1 comma T2 belongs to R. That means this condition is satisfied. A comma A belongs to R. So therefore, T1 is congruent to T1. Therefore, R is a reflexive. So since every triangle is congruent to itself, that is T1 is congruent to T1. So T1 comma T2 belongs to R implies T1 is congruent to T1. That is the condition A comma A belongs to R is satisfied. Therefore, R is a reflexive. Now let us come to the second one. Reflexive, then it is symmetric. Verify whether it is symmetric or not. Now the second condition, symmetric relation. R is symmetric since T1 and T2. Suppose if T1 and T2 are any two triangles, see if this is triangle T1 and this is T2. If T1 is congruent to T2, then T2 is also congruent to T1. So here R is symmetric since T1 comma T2 belongs to R implies T2 comma T1 also belongs to R. That is A comma B belongs to R implies A comma B belongs to R implies B comma A also belongs to R. T1 comma T2 belongs to R implies T2 comma T1 also belongs to R. That is the triangle T1. T1 is congruent to T2 implies T2 is also congruent to T1. T1 is congruent to T2 implies the triangle T2 is also congruent to T1. That means T1 comma T2 belongs to R implies T2 comma T1 also belongs to R. So therefore R is a symmetric. Okay. Now let us come to the third, transitive property. If R is transitive, since T1 comma T2 belongs to R and T2 comma T3 belongs to R implies triangle T1 and T2 or T3 also belongs to R. That means if T1 is first triangle is congruent to the second triangle T2 and T2 is congruent to the third triangle T3, which implies the first triangle is also congruent to the third triangle. Suppose if these are the three triangles, if T1, T2 and T3. So this is congruent. So if T1 is congruent to T2, T2 is congruent to T3 implies the triangle T1 is also congruent to T3. So T1 is congruent to T2 and T2 is congruent to T3 triangle. The first triangle T1 is also congruent to T3. Therefore, this is transitive relation. That means here A comma B belongs to R and B comma C belongs to R implies A comma C also belongs to R. That means T1 is congruent to T2 and T2 is congruent to T3 implies T1 is also congruent to T1, T3, T1 is also congruent to T3. So therefore it is a transitive relation. Since this satisfies all the three relations, so since R satisfies reflexive, symmetric and transitive, therefore R is an equivalence relation. Suppose in the examination they may ask, define equivalence relation, give an example, or give an example for an equivalence relation, means you can write this itself is enough. So let T be the set of all triangles in a plane with R a relation in T given by R is equal to T1 comma T2, that is T1 is congruent to T2 is an example for an equivalence relation which satisfies all the three conditions, reflexive, symmetric and transitive. That's it. Okay. So this is very important for 3 marks. Hope you followed what is a relation, what is equivalence relation and how to solve an equivalence relation. Now let us come to the set of problems now, 3 marks questions. Let L be the set of all lines. L is the set of all lines in a plane and R is relation in L denoted by R is equal to L1 comma L2 such that L1 is perpendicular to L2, show that R is symmetric but neither reflexive nor transitive. Now, the set of all perpendicular lines is an example for a relation which is symmetric but neither reflexive nor transitive. So, in the examination they may ask, give an example for a relation which is symmetric but neither reflexive nor transitive, means right away you can say the set R, the relation R on the set L defined by R is equal to L1 comma L2 such that L1 is perpendicular to L2 is an example. Now, let us come to the first. Let me check whether it is equivalence or not. Now, let reflexive. What is reflexive? A comma A belongs to R. For all A comma A belongs to R, then A is related to R is called reflexive. Check whether R is not reflexive relation, because since L1 cannot be perpendicular to itself, suppose if a line is perpendicular, this cannot be perpendicular to itself. L1 is not perpendicular to the line L1. So, R is not reflexive. Since L1, the line 1 cannot be perpendicular to itself, therefore, L1 comma L1 does not belongs to R, because L1 is not perpendicular to L1. So, therefore, this is not a reflexive. L1 comma L1 does not belongs to R. See, this is L1 cannot be perpendicular to the same line. Okay. Now, therefore, this is not a reflexive. Now, let us come to the second one, reflexive, then symmetric. What is symmetric? R is symmetric. So, as here, as the line L1 is perpendicular to L2, L2 is also perpendicular to L1. See, here this is the line L1 is perpendicular to L2 and this line L2 is also perpendicular to L1. That means we can say that R is symmetric as L1 is perpendicular to L2, then L2 is also perpendicular to L1. So, if L1 is perpendicular to L2, this L2 is also perpendicular to L1. So, therefore, this is a symmetric relation. So, R is symmetric as L1 is perpendicular to L2 implies L2 is also perpendicular to L1. That is L1 comma L2 belongs to R implies L2 comma L1 also belongs to, that is if A comma B belongs to R implies B comma A also belongs to R. Therefore, R is a symmetric relation. Further, check whether it is transitive or not. R is not transitive because L1 is perpendicular to L2 and L2 is perpendicular to L3, then L1 cannot be perpendicular to L3. If L1 is perpendicular to L2 and L2 is perpendicular to L3, then this L1 is not perpendicular to L3. So, therefore, L1 comma L2 belongs to R and L2 comma L3 belongs to R implies L1 comma L3 does not belongs to R. So, only symmetric but not reflexive and transitive. Okay. Now, let us come to the next problem. What is the problem? Show that the relation R in the set 1, 2, 3 given by R is equal to 1, 1, 2, 2, 3, 3, 1, 2 and 2, 3 is reflexive but neither symmetric or transitive. Now, this is also an important example. So, we have to verify whether the given relation is only reflexive but neither symmetric nor transitive, and the relation is given by these are the elements. On the set A, what is A? A is equal to 1, 2, 3. And what is the relation given? R is equal to 1, 1, 2, 2, 3, 3 and again 1, 2 and 2, 3. Now, just by looking through the relation, you can say that R is reflexive because 1, 1, 2, 2, 3, 3 belongs to the R. So, first you can say R is reflexive. R is reflexive because 1, 1 belongs to R, 2, 2 belongs to R and 3, 3 also belongs to R. That is A belongs to R. Okay, reflexive property is satisfied. Now, let us come to the second one, symmetric. Symmetric relation, symmetric property. So, here 1, 2 belongs to R implies 2, 1 does not belongs to R. 1, 2 is there, but 2, 1 is not in the set. Okay, so does not belongs to R. So, therefore, R is not symmetric. This is not symmetric. That is, 1 comma 2 belongs to R, but 2 comma 1 does not belong to R, therefore R is not a symmetric. Now check whether it is transitive or not. Now what is the transitive property? Transitive. What is transitive property? If A comma B belongs to R and B comma C belongs to R, implies A comma C also belongs to R. Okay, now check whether transitive or not. So let us take these two elements. 1 comma 2 belongs to 1 comma 2 belongs to R, and 2 comma 3 also belongs to R. 2 comma 3 belongs to R, implies 1 comma 3. 1 comma 3. See, 1 comma 3 is not in the set, does not belongs to R. So here A comma B belongs to R, B comma C belongs to R, implies A comma C does not belongs to R. So does not belongs to R. 1 comma 2 belongs to R, 2 comma 3 belongs to R, but 1 and 3 does not belongs to R. So therefore R is not a transitive. Not transitive. So we can say that this relation R is only reflexive but neither symmetric nor transitive. Okay. So if you do this much, you will get 3 marks for this. Very simple problem. Followed? Okay. Now let us come to the next problem. Show that the relation R in the set. So a relation R on the set Z, set of all integers given by R is equal to A comma B, such that 2 divides A minus B is an equivalence relation. This is also an important problem for 3 marks. Show that the relation R on the set Z of all integers given by R is equal to A comma B, such that 2 divides A minus B. A comma B such that 2 divides A minus B is an equivalence relation. Now let us come to the solution. Equivalence relation means it should be reflexive, symmetric and transitive. Now what is to verify? Verify whether it is reflexive, symmetric and transitive, then we can say that it is equivalence relation. Now let us verify the first one, reflexive relation. R is reflexive as 2 divides A minus A. What is A reflexive? A comma A belongs to R, implies A minus A will divides 2. So 2 divides A minus B, that is 2 divides 0, right? So therefore R is reflexive as 2 divides A minus B for all A belongs to Z, because 2 divides 0, therefore R is a reflexive on Z. So A comma A belongs to R implies 2 divides A minus A, that is 2 divides 0. So 2 divides 0, therefore R is a reflexive property. Reflexive condition is satisfied on Z. Now let us come to the second, symmetric. Verify whether it is symmetric or not. What is symmetric? If A comma B belongs to R and then A comma B belongs to R, then B comma A also belongs to R. That means according to the condition, if 2 divides A minus B, then 2 also divides B minus A. See, if 2 divides A minus B, then 2 divides B minus A also, right? Suppose if A comma B 2 divides A minus B, implies then this 2 also divides B minus A. So therefore, so if 2 divides A minus B means then 2 also divides B minus A. Therefore, A comma B belongs to R implies B comma A also belongs to R. Therefore, it is a symmetric. Say, for example, let us take for example, if A is equal to 4 and B is equal to 6, then if 2 divides 4 minus 6, that is 2 divides minus 2, right? 2 also divides 6 minus 4, that is 2 divides plus 2. Okay, so that means if 2 divides A minus B means then 2 also divides B minus A. If 2 divides A minus B, then 2 also divides B minus A. Therefore, A comma B belongs to R implies B comma A also belongs to R, means R is a symmetric. Now let us come to the third one, that is the transitive property. What is transitive property? If A comma B belongs to R and B comma C belongs to R, implies A and C belongs to R. That is, if 2 divides A minus B and 2 divides B minus C, then it will also divide A minus C. 2 also divides A minus C. See here, if 2 divides A minus B and 2 divides B minus C, then 2 also divides A minus C. So if 2 divides A minus B and 2 divides B minus C, which implies 2 divides A minus C also. If 2 divides A minus B and 2 divides B minus C means 2 also divides this So that is 2 also divides A minus C, that is A minus C. A minus C can be written as A minus B plus B minus C. So 2 also divides A minus C. Therefore, R is transitive. So hence R is, here the given relation R is reflexive, symmetric and transitive. Hence R is an equivalence relation. This is also an example for equivalence relation. Okay, right. Now let us come to the next problem. So this is very important problem. You may expect this type for your final examination. Very important problem. What is the problem given? Determine whether the relation R in the set A is equal to 1, 2, 3, 4, etc. up to 14, 13, 14, defined as R is equal to x comma y such that 3x minus y is equal to 0 is reflexive, symmetric and transitive. Now we have to verify whether the relation is reflexive, symmetric and transitive. What is the condition given? R is x comma y such that 3x minus y is equal to 0. So if you multiply first element by 3 and subtract the second element, that is equal to 0. So very simple. What is given? R is equal to x comma y such that 3x minus y is equal to 0 means R is equal to x comma y such that 3x minus y is equal to 0 means y is equal to 3x. So the elements here are 3x minus y is nothing but y is equal to 3x. So we can write the relation R as x comma 3x. So write down R is equal to, first element is 1, multiply with 3, 1 comma 3. See, so here this condition will be satisfied. 1 into 3 is 3, minus 3 is equal to 0. Second, next 2 comma 3 2s are 6. Here first element is multiplied by 2, 2 into 3 is 6, minus 6 is equal to 0. Again 3 comma 9, then 4 comma 3 4s are 12. Now you cannot take 5, and because 5 3s are 15, but 15 does not belongs to the given set, that is, what is it given? On the set A, does not belongs to A. So we cannot take this. Okay. So therefore the elements of the relation R are 1 comma 3, 2 comma 6, 1, 3 comma 9 and 4 comma 12. Now verify whether this will satisfy all the three conditions. By looking to the problem, you can say that this is not reflexive because 1 comma 1, 2 comma 2, 3 comma 3 does not belongs to R, not reflexive. Symmetric, 1 3 is there but 3 1 is not there, 2 6 is there, 6 2 is not symmetric. Transitive, 1 comma 3, 3 comma 9 is there but 1 comma 9 is not there, therefore it is not a reflexive, symmetric and transitive, therefore this is not an equivalence relation. Now let us verify one by one. Now first one, I will go to the next page. R is equal to, what is the relation we have? 1 comma 3, 2 comma 6, then 3 comma 9 and 4 comma 12. Now one by one. First one, reflexive. Reflexive. Verify. R is not reflexive. R is not reflexive. R is not reflexive because 1 comma 1 does not belongs to R. That is, A comma A does not belongs to R. 1 comma 1, 2 comma 2, 3 comma 3 does not belongs to R. Therefore, R is not reflexive. Second one, symmetric. Symmetric. R is not symmetric. R is not symmetric because 1 comma 3 belongs to R. 1 comma 3, since 1 comma 3 belongs to R, implies 3 comma 1 does not belongs to R. Right. See, 1 comma 3 is there but 3 comma 1 is not there. So that is A comma B belongs to R, implies B comma A does not belongs to R. So R is not symmetric. Now the third one, let us come to the third one, transitive. Transitive relation. What is transitive? Let us consider these two. 1 comma 3 belongs to R and 3 comma 9 belongs to R, implies 1 comma 3, 1 comma 9. See, 1 comma 9 does not belongs to R. So 1 comma 3 is there, 3 comma 9 is there, but 1 comma 9 does not belong to R, therefore R is not transitive. R is not transitive. That is, A comma B belongs to R and B comma C belongs to R implies A comma C does not belong to R. So therefore R is not transitive. So the given relation is neither reflexive, symmetric or transitive. So this is not an equivalence relation. R is not reflexive, R is not symmetric, R is not transitive. Hence this is not an equivalence relation. That's it. Very important problem indeed. Okay, hope you followed. Very simple problem. Now let us take a similar type problem. Let me solve one more similar type problem. Now let us take this problem. Determine whether the relation R in the set of natural numbers n defined by R is equal to x comma y such that y is equal to x plus 5 where x is less than 4 is reflexive, symmetric and transitive. Okay. Now let us come to the solution. What is given? R is equal to x comma y such that y is equal to x plus 5 and x is less than 4. That means here x comma y is nothing but x and y is nothing but x plus 5. X comma x plus 5. And the elements of x can be taken as 1, 2 and 3. So therefore R is equal to, when x is equal to 1, 1 plus 4, 1 plus 5 it is 6. When x is equal to 2, 2 plus 5, 2 plus 5 is 7. When x is equal to 3, 3 plus 5 is equal to 8. So these are the elements. 1 comma 6, 2 comma 7 and 3 comma 8 are the elements of the set. Okay. Now see here, therefore the elements of the set are 1 comma 6, then 2 comma 7 and 3 comma 8. Now verify whether it is reflexive, symmetric or transitive. First one, reflexive. Reflexive. What is reflexive? A comma A belongs to R. Here 1 comma 1, 2 comma 2 does not belong to R. 1 comma 1 does not belong to R. So therefore R is not reflexive. R is not reflexive. Here 1 comma 1, 2 comma 2, 3 comma 3 does not belong to, so therefore R is not reflexive. Symmetric. What is R we have? R is equal to 1 comma 6, 2 comma 7 and 3 comma 8. Now second property, symmetric. Symmetric. Here 1 comma 6 belongs to R implies 6 comma 1 does not belongs to R. That is A comma B belongs to R implies B comma A does not belongs to R. So therefore R is not symmetric. This is not symmetric. R is not symmetric, not reflexive, not symmetric. Now let us verify the transitive property. Transitive property. What is transitive? If A comma B belongs to R and B comma C belongs to R implies A comma C belongs to R. Now let us take any element. You can't take 1 comma 6, A comma B, B comma. So therefore by just looking to the problem we can say that A comma B belongs to R, B comma A belongs to R implies A comma C does not belong to R. Therefore R is not transitive. R is not transitive. So hence this is neither reflexive, symmetric and transitive. That's it. Now let us come to the next problem. Now examine whether the relation R on the set A is equal to 1, 2, 3, 4, 5, 6 defined as R is equal to x comma y such that y is divisible by x is a reflexive, symmetric and transitive. Okay. Now let us take this problem. Now what is given? R, the relation R is equal to x comma y such that y is divisible by x. Y is divisible by x. Okay. Now write down the elements of the set R. R is equal to, what is A? 1, 2, 3, 4. Again A is equal to 1, 2, 3, 4, 5 and 6. So here what is the condition? Y is divisible by x means that second element is divisible by the first element. So y is divisible by x. Now let us take 1 comma 1, 1 comma 1, then 1 comma 2, 1 comma 3, 1 comma 4, 1 comma 5, 1 comma 6. So you can divide 2, 3, 4, 5, 6 by 1. Now let us come to the second. So 2 comma 1. So you cannot divide 1 by 2. 2 comma 2. 2 is divisible by 2. 2 does not divide 3. 2 comma 4. You can divide 4 from 2. 2 is not divisible by 5. 2 comma 6. So you can divide 6. Similarly, come to the third element. 3 comma 1 not possible. 3 comma 2 not possible. 3 comma 3. So 3, 4 is not possible. 3, 5, 3, 6. You can divide 6 by 3. Now again similarly from 4. 4 comma 1, 4 comma 2, 4. So not possible. 4 comma 4. You can divide 4 from 4. 4 comma 5 not possible. 4 and 6 is also not possible. Again from 5. 5, 1, 2, 3, 4. Nothing will possible except 5 comma 5. You can't divide 6 by 5. Now again 6 from 6. You can't divide all the elements except 6 comma 6. So the elements of the set are, so 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4, 1 comma 5, 1 comma 6, 2 comma 2, 2 comma 4, 2 comma 6, 3 comma 3, 3 comma 6, 4 comma 4, 5 comma 5, 6 comma 6. Now just by looking through this, we can say that 1 comma 1 belongs to 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4, 5 comma 5, 6 comma 6 belongs to R. Therefore R is reflexive. Okay. Now we can say that R is reflexive. Therefore R is reflexive. R is reflexive because A comma A belongs to R. That is, see here 1 comma 1 belongs to R. Similarly, 2 comma 2 belongs to R, 3 comma 3 belongs to R, 5 comma 5, 4 comma 4, 6 comma 6 all belongs to R. So therefore, first condition is satisfied. R is reflexive. Now let us come to the second one. Second, reflexive, symmetric. Verify symmetric, whether it is symmetric or not. See, 1 comma 3 belongs to R, 3 comma 1 does not belongs to R, 1 comma 3 belongs to R implies 3 comma 1 does not belongs to R. Similarly, you can take 1 comma 4. See here, 1 comma 4 belongs to R implies 4 comma 1 does not belongs to R. So therefore, R is not symmetric. Not symmetric. This is not symmetric. Now verify the third property, that is third one, transitive property. Transitive. So let us take any element. So you can take 1 comma 2 belongs to and 2 comma 4 belongs to R implies 1 comma 4 also belongs to R. So 1 comma 2 belongs to R, 1 comma 2 belongs to R, and again 2 comma 4 belongs to R, 2 comma 4 belongs to R implies so 1 comma 4 also belongs to R. So hence it is a transitive. So if you consider this example, 1 comma 3 belongs to R and then 1 comma 3 belongs to R and 3 comma 6 belongs to R implies 1 comma 6 also belongs to R. So hence we can say that R is reflexive and transitive but not a symmetric. Okay. Now let us come to the next problem for 2 marks. Show that the relation R on the set 1 comma 2 comma 3 is given by R is equal to 1 comma 2 2 comma 1 is symmetric but neither reflexive nor a transitive. So what is reflexive? Reflexive means A comma A belongs to R. This implies 1 comma 1 does not belongs to R and 2 comma 2 also does not belongs to R. So therefore R is not reflexive. This is not reflexive. Second one, so show what is to show? This is only symmetric. R is symmetric. R is symmetric. R is symmetric because see here 1 comma 2 belongs to R implies 2 comma 1 also belongs to R. That is A comma B belongs to R implies B comma A also belongs to R. Therefore R is symmetric. So R is symmetric. And let us verify the transitive property. R is not transitive. R is not transitive because A comma B belongs to R and B comma C belongs to R implies A comma C does not belongs to R. Okay. Now therefore this is not a transitive. Therefore it is symmetric but neither yes, symmetric, but neither reflexive nor transitive. Okay. Now let us come to the next problem. Give an example for a relation which is symmetric but neither reflexive nor transitive. Now we have to give an example for a relation which is symmetric but neither reflexive nor transitive. Now let us define the solution like this. Now we have to give an example for a relation which is symmetric but neither reflexive nor transitive. Previous problem itself is an example. Or let us take let us consider a set A is equal to A comma B comma C. On a set A, let us define the relation R is equal to A comma B and B comma A. This is the relation. This is an example for a relation which is, see, it is not reflexive, not reflexive because A comma A does not belongs to R, and this is symmetric. This is symmetric because A comma B belongs to R implies B comma A also belongs to R, and this is not transitive. A comma B belongs to R and B comma C belongs to R implies A comma C does not belongs to R. So R is not transitive. So this is an example for a relation which is symmetric but neither reflexive nor transitive. That is, define a relation R on a set A is equal to A, B, C by R is equal to A comma B and B comma A is an example for a relation which is symmetric but neither reflexive nor transitive. Okay. Now let us come to the next problem. Give an example of a relation which is transitive but neither reflexive nor symmetric. Now same type, let us consider a set let A is equal to A comma B comma C be any non-empty set. Then define a relation R on A, that define a relation R on A as R is equal to A comma B, B comma C and A comma C. Let us define a relation R is equal to A comma B, B comma C and A comma C. So clearly we can say that here R is not reflexive. R is not reflexive because A comma A does not belongs to R. R is not reflexive. And give an example which is transitive but neither reflexive nor symmetric. And R is not symmetric. R is not symmetric. See, because A comma B belongs to R implies B comma A does not belongs to R. B comma A does not belongs to R. Now verify whether R is transitive. A comma B belongs to R and B comma C belongs to R implies A comma C belongs to R. See, A comma B belongs to R and B comma C belongs to R implies A comma C belongs to R. So R is not reflexive, not symmetric, but R is transitive. So this is an example for a relation which is transitive, neither reflexive nor symmetric, which is transitive but neither reflexive nor symmetric. Okay. Now let us come to the next type, same type problem. Give an example for a relation which is reflexive and symmetric but not transitive. Reflexive and symmetric, not transitive. Now same, let us consider a set. Let A is equal to the same A comma B comma C. Let us consider a set A is equal to A, B, C. Define a relation R on A as R is equal to, let us write the elements A comma A, B comma B, C comma C. Okay, and A comma B and B comma A, and B comma C and C comma B. Now let us define the relation like this. Now verify whether it is, first one by one, reflexive. R is reflexive because A comma A belongs to R, B comma B, C comma C all belongs to R, therefore it is reflexive. So which is reflexive. And symmetric, verify whether it is symmetric. Symmetric property. What is symmetric? R is symmetric. R is symmetric because see here A comma B belongs to R implies B comma A also belongs to R. A comma B belongs to R implies B comma A also belongs to R. B comma C belongs to R implies C comma B also belongs to R. And the third one is transitive. Transitive. What is transitive? A comma B belongs to R and B comma C belongs to R implies A comma C does not belongs to R. So therefore, R is not transitive. So this is an example for a relation which is reflexive symmetric but not transitive. See, reflexive A comma A, B comma B, C comma C belongs to R. Symmetric A comma B implies B comma A or A comma B comma C implies C comma B, and not transitive because A comma B belongs to R, B comma C belongs to R implies A comma C does not belong to R. Therefore, this is not transitive. Hence, it is an example for a relation which is reflexive, symmetric but not transitive. Okay. Now, let us come to the problem. Give an example for a relation which is reflexive and transitive but not symmetric. Now, let us define a set A is equal to A. Let us consider a set A. On the set A, define the relation R is equal to A comma A, B comma B, C comma C, and A comma B, B comma C, and A comma C. Now let us define a relation R is equal to A comma A, B comma B, C comma C, A comma B, B comma C, and A comma C. Now clearly you can say that R is reflexive. R is reflexive because all A comma A belongs to R, B comma B, C comma C all belongs to R. Reflexive. Symmetric. Verify the property of symmetric. Symmetric. R is not symmetric here. Not symmetric because A comma B belongs to R implies B comma A does not belongs to R. B comma C is there, C comma B does not belong to R. A comma C is there, C comma A does not belong to R. So therefore R is not symmetric. Let us come to the transitive property. Transitive. R is transitive. R is transitive. R is transitive because A comma B belongs to R and B comma C belongs to R implies A comma C also belongs to R. So therefore this is transitive. Hence this is an example for a relation which is reflexive transitive but not symmetric. Okay. This is how we are going to solve the problems based on reflexive, symmetric and transitive. Hope you followed. You just practice, then you will have an idea. So these type of problems are very, very important for the point of examination. So that's all regarding today's session. Let us meet with a different concept in the next session. Don't miss the class. Thank you very much.